Okay, so today we're talking about scale and similarity. So we're doing similar solids, but I'm going to start with similarity in each dimension. We're going to talk about what happens to these shapes as we scale them up. So starting with one-dimensional shapes. So something that can only be measured in one direction, forwards and backwards. That would give us the line here. And let's just give ourselves some numbers to work with. I know that we like to see numbers. So if we call this line 10 units long, and let's say we want to scale it up, and we're going to use some scale factor. Let's just say that the scale factor today we're going to start with 2. We'll try some other ones. So if I start with a scale factor 2, that means that I'm going to double how long this line is. And I think that that's easy enough to see. You guys are probably used to this. That if I double the length, I'm going to end up having 20 as my final answer. So basically what you've done is you've had your original 10, okay, we'll call that L in this case. We've had our original L, and we've multiplied it by our K, which was 2 in this case, to the first power. Okay, K to the first power. And this is going to be the one-dimensional scale. We're scaling it up in one direction, one dimension. So now, what happens if we wanted to scale it up, let's say, in 2 dimensions? So we have, let's say, this rectangle here, whose measures would be 10 and 4, if you will. So when I scale this up, I'm going to scale it up in 2 dimensions, which means when I double it, I've not only had to double it in the direction of 10, so that I get 2 of those. Here's my first 10 and here's my second 10. But you know what? That doesn't make sense if I don't double it in the 4 direction also, because, I apologize. I need to double it in the 4 direction as well, so that I can actually get a scaled up version of this. They need to be similar. And to be similar, we've talked about in proportions, to be similar, I need to have a consistent ratio from the starting length here with 10 to the ending length of 20. Okay, we said this is going to be 20, and this will be equal to 8. Well, 10 doubles to 20, and 4 doubles to 8. So that works. We've got a consistent proportion of sides, and all of the angles are still the same angles that they were before. So we do have similar objects. So what we find is that this length L that was 10 and the width W that was 4 are both going to get multiplied times K to the first. And the W is multiplied by K to the first. However, those lengths are just one-dimensional because length is only measuring this one dimension. Width is only measuring this one dimension. So what measurement measures in 2 dimensions? Well, that would be this measurement we call area. And you find the area of one of these shapes, and right now we're using a rectangle, by multiplying our 2 measurements that are at 90 degrees from each other, so length and width in this case. We're going to multiply those together. So in this case, I'm going to multiply these, and I'm going to get L times K times 1, or to the 1 power, times W times K to the 1 power. Well, I can't really mix the L and the K and the W, but I can just get L times W times K to the 1 times K to the 1. And you guys probably remember that when you multiply like terms, you add their bases, or sorry, add their exponents. When you multiply like bases, you add their exponents. So I'm going to end up having that the answer is K to the 2 times length times width. And length times width, we understand this was the formula for area, right? So what we really get is the K to the 2 times area. So the area was that 40 that we would have originally had. So let's look at the area over here. Let's find out if this is true. Our K, we said, was 2 in this case. So K squared is 4. So this should be 4 times the original area we had of 40. 4 times 40, that's 160. Let's find out if that actually happened here. So what do we get in our problem? We said that this is going to be 20 now, and this is going to be 8. And so I'm going to get that the area is equal to 20 times 8. That's not 4 times 40, but it is 160 square units. So this area is going to be multiplied by a factor of k to the 2 power, k squared. So our factor is getting squared. And the way I like to remember it is that in 2 dimensions, you are going to get a square. Just like in 1 dimension, you had to the first power. All right, so let's see how this is going to play into 3 dimensions. And I think you guys can probably guess at this point how this is going to look. That I'm going to have to erase some of this stuff. So let me move to the next page. All right, so in 3 dimensions, I'm going to need to scale this thing up. Oh, I believe I forgot the pattern I need to do here. Let me undo this. To scale this up, I'm going to make it twice as wide. But hey, I also need to make it twice as deep. And I finally need to make it twice as tall. All right. So let's see if this thing is proportional, if it's similar. So following our previous ones, we said that it needs to be double in all directions. So before we said L becomes double L. And here we said that L should become double L, but W should also become twice W. So in this case down here, if I've got length and I've got width, and let's call this measurement here, front to back, depth, then have I made it twice as long? Well, it looks like it. L plus L equals 2L. Have I made it twice as wide or twice as tall? Sure, W plus W equals 2W. And have I made it twice as deep? Twice as deep. So if I go down here, there's 1D, and there's another D. So add those together, and I get, yeah, twice the depth. So this is going to be a similar shape because I have got twice the length, twice the width, and twice the depth. That means it is proportional to the power, to the scale factor of 2. So what about the measurements of it? We talked about just length in the one-dimensional shape, and here we had to talk about area because length is just a one-dimensional measurement and area is a two-dimensional measurement. Now we could talk about what happens to the surface area of this box, but that's not the similarity that we're trying to talk about today because that's going to be a little bit different. But right now what we want to talk about is what happens to the volume of this box. We want to think 3D right here. Okay, it's going to be pretty easy to see what the surface area does. It's going to be very similar to the previous one. If I had one top up here, I'm going to have 4 of them now. So it's going to be 4 times or 2 squared times. So it's going to go back to our previous work that we did with the area. But right now, let's talk about the volume. What happens to the volume of this? So what was going to be length times width times depth, and let's give this some numbers because I know how we all like our numbers here. So let's just call this 10, and we'll call this height 2, and we'll call this depth 3. So when I double this 10, now I'm going to have something that is 20. And the depth, when we double that, 3, I'm going to get something that is 6 tall. And then, or deep. And then when I double this width that is 2, I'm going to have something that's 4 deep. So when I look at what happens to to the volume formula. Remember our basic volume formula we've been working with is the area of the base times the height of the solid. Okay, the perpendicular height of the solid. So that means if I look at it, and I can pick any side to be the base that I want to, but let's go with the 10 and the 3. So the area of the base is going to be length times width, which is 10 times 3, times the height of this solid, which is going to be 2, is going to end up being the original shape is going to have an area of 60 units cubed. So now what about the volume of the new shape? Well, if we take a look at what happened to the equation, the volume of the new shape is going to get the area of the base times the height of the solid. Okay, well, what happened to the area of the base? The base is no longer 10 times 3. The base is going to be twice 10 times twice 3 times the height is going to be changed to twice 2. And we got those numbers over here. We said twice 10 was 20. We said twice 3 was 6. And we said twice 2 was 4. So when we multiply that together, I'm just going to pull these 2's out because I want you to see what happens. If I pull these 2's out to the front, I'm going to get 2 times 2 times 2. Let's put that together in this little parentheses. And then what's left? Oh, well, the 10 is left, the 3 is left, and the 2 is left. So those 3 are left. After I pulled out those 3 2's, I just wanted you to see that, look, this 10 times 3 times 2 is the same 10 times 3 times 2 we had up here. That gave us 60. So what I'm really seeing is this 2 times 2 times 2, or 2 cubed, times the original 60. Which ends up being 8 times 60, which is 480 units cubed. So we look at this and we say, look, we doubled the size of the shape, but what happened to the volume? The volume went from 60 up to 480. I don't know if any of you guys are doing your calculator work right now, but that's more than doubled. So we're looking at what happens to this scale factor here of 2. It's no longer just double, it's double, double, double. And that's 2 cubed. So really it's multiplied by 8 in this case. Now, that's going to change whether we're talking about 2, if we're going to double something or triple something. So we're going to look here real quick at what happens to tripling something. So let me clear all the work on this page. And let's say we want to go about tripling this object. So what if I tripled the size of this object? So it's going to be, let me move that one over a little bit. It's going to be 3 times wide. Okay. It's going to be 3 times tall. Good night. There's a lot of them here. And we can't forget, it's got to be 3 times deep. 3 times as deep. Oh, I made a mistake. I always got to start on the right. Fill in or it doesn't layer right. Just the tricks of the trade. And it does kind of snap for me, but I don't always hit the snap. So it might look like a lumpy shape as I'm working on this. Okay. So here's what we've got. We've got this box that has been created 3 times as tall. So what was 10, and we said this was 3, I believe, and this was 2, has now become 30. And this height of 2 has become 2 plus 2 plus 2, 6. And this depth of 3 has now become a depth of 3 plus 3 plus 3, so 9. So what is happening here is our K has changed. It's no longer 2. The K is 3. So before we do this with just the numbers, let's look and see if we can figure out what's going to happen. We notice that the volume is going to be equal to the area of the base times the height. And before we said that, hey, there is some K at work here, and we notice that it's going to end up having the same volume, but it's going to be multiplied by something. So let's say the volume of K, the volume of the one that's been expanded, it's been scaled up or scaled down, is going to have some factor affecting it times that original volume. So some number of those original volumes. And this is going to be K cubed in this case, K cubed. And I get the cube from the fact that it is 3 dimensions. This is the 3-dimensional part of it. And the reason it's K cubed is because what's really happened, let's just use a simple formula like length times width times height. The original length times width times height have all been multiplied by the same K. So it's no longer the simple original one. It is V equals K times length times K times width times K times height. So you notice the original length, width, and height that we had, but there's 3 K's now in front. And so if I pull those 3 K's out to the front, I end up getting K cubed times that original length times width times height that we got from doing the shape. So this is where that K cubed is going to come in. It's going to come in from the fact that we've actually scaled up each direction, each dimension, we've scaled it by K. And in this case, it doesn't really matter what K is, but in this case, K is 3. Okay, but K could have been 3.2, and this still works. You would just have to cube 3.2. But it wasn't 3.2, so we're going to take that out. It was 3. So we need to think, what is 3 cubed? So the volume of this should be 3 cubed times the original volume. So the volume of K is 3 cubed times the original volume. I don't know what the original, well, actually we do know what the original volume is. We learned it on the last one. The original volume was 60 units cubed, right? So that's what the original volume was. So we know that we should end up just trying to find what 3 cubed is. And we're going to get the volume after scaling it up. 3 cubed is 27 times 60 units cubed. Oh man, 27 times 6. That's going to be 120 plus 42. So what, 162 with another 0. So is that 1,620 units cubed? Forgive me if I get my math wrong. So let's find out if that is what really happened. That's what we believe is going to happen using this idea of K cubed. So let's try it with the math and see what really happens. Over here we can see that the volume of K, this is what we're going to call K here, this big box. The volume of K is 30 for the length of the base times 9, so that's that width of the base, times how high we're going to stack it. We're going to stack it 6 tall. And let's see what ends up happening. Well, 9 times 6 is 54. 30 times 54. And let's see, 3 times 50 is equal to 150. And 3 times 4 is equal to 12. So 150 plus 12 is 162. But don't forget my other 0 there. So 1,620. Yeah, it worked. Okay, so 1,620. So we're seeing that we can utilize this K without even needing to find these three numbers. So as long as we have the original shape and we know what the scale factor is, then we can skip down here to using this k cubed idea, and we can get to the answer without having to go through and actually find the three new lengths. All right, and surface area though. Surface area is going to go back to what we talked about earlier with the area of the shape. So let's take a look at that right real quick before we're done. Let's look at the surface area and see what happens. So with the surface area, we once again have our let's see, 10, 3, and 2, which I want you guys to think more in terms of just length, width, and height, because that's going to be much more helpful here. So when I scale this up, let's say in the case of k equals 3, like we've done here, when I scale this up and I look at what happens, my L, or 10, is going to become 3 times L. Okay? And in this case, I know you guys like your numbers, so that's what, 30? Okay? And then my H is going to become 3 times H. Okay? And let me put parentheses over here so you don't think that's 2 times H. That probably even makes it worse. Here. Let's just do this. H equals 2. That's probably the better way to write that, right, Mr. Conaway? Yes. You need to be more diligent, Mr. Conaway. Okay, and so this, what was W, is going to be 3 times W, okay? And so that is equal to 30. That is equal to, in this case, 3 times H was 2. So that's going to be equal to 6, and then 3W was equal to 9. So let's look at what's happening to the surface area. So the surface area, we need to find the area of each surface. This is one large rectangle. No, it doesn't look like a rectangle. It's just because of perspective. It is a rectangle, and it's a rectangle with 9 and 30 as its sides, or as I would prefer to look at it, okay, so the area of the top and the bottom, okay, is equal to, I'm going to look at this as a rectangle with a side of length and width, but in this case, it's a side of 3 lengths. 3L times 3W. So that's actually going to get multiplied to be 9LW. But I want to even make this, no, I don't even like this. No, I don't like this. You know what I want to do? I want to use K. Because if I can use K, I hit the wrong button. Go away. I hit the wrong button. If I can use K, then I can do this for any number of K, and I don't have to just stop whenever it's 3 and use 3 every time. So instead of doing this with 3 times L, I'm going to say this is KL, and this is KW, and this is KH. And so let's try that here. I'm going to get KL times KW. Okay, so that gives me K times K is K squared. L times LW. Well, you know what? LW looks really familiar. That's just the length and width. That's the area of the top of the thing originally. That's this area over here that I originally had when I said length, length times width, and I got this area. So what I'm saying is I'm going to get K squared times that LW for just the top. Okay, so the top and bottom are both that. And how about the left and right? Area of the left and right side. Well, that's going to be, let's see, the left and right side has H and W involved. So that's going to be KH times KW, whatever K is. It was 3 in this case, but I'm just using K so we can see it in general. K squared times HW. So that tells me that I'm just going to need to multiply whatever my original side was, H times W, I need to multiply it by K squared. And finally, let's do the area of the front and back. The area of that front and back, well, let's see, that front and back that is going to be h tall by L long. So that's going to be KH's, that's the new H, and that's going to be KL's. So when I multiply that, that's going to give me K squared times HL. So really, this was that original HL that would have given us this face of the shape, is now going to be multiplied by K squared to get this face of the new similar shape. And the blue one over here that we marked is going to be multiplied by K squared to get this face. And the black one is going to be multiplied by K squared to get this face. Okay, so after we go through and multiply all these by K squared, now let's talk about adding the surface areas up. So over here, we had, let's see, the area of the top and bottom was originally, and I should do this in black so that I'm following my pattern here. The original area of the top and bottom was length times width. Okay, the original area of left and right, and I'm talking about this shape over here. Okay, the original area of left and right equals height times width. And the original area of front and back equals height times length, or length times height. Now to get the surface area, we know that we had to add all these together. But hey, there's two of these. There's one for top, one for bottom, one for left, one for right, one for front, one for back. So when I add all these together, I'm going to get two length width plus height width plus length height. Okay, I think that's a formula out of your book right there. So the surface area is going to be equal to 2 of those added together. So let's see what I get when I do the new one. The new one over here, when I do the surface area, I'm going to need 2 of all of these. So 2 times K squared length width plus K squared HW plus K squared HL. And I don't know if you remember from Algebra 1, but you're supposed to, if you see something like this that's consistent through all of them, we're going to do what's called factoring. So we're going to carry that factor all the way to the front for ourselves here, just so we can see what's happening. So the surface area, and we're going to call it surface area K, the surface area after it's been modified, is going to put that K squared right out front. We're pulling that sucker all the way out front. And then we're going to see that there's 2 times the LW plus the HW plus the HL that we saw before. And finish that off. So if we look at it, this is really the same as this. So why don't I just get rid of all that and get rid of all this and replace it with what it is? What did this thing stand for? It stood for surface area of the original object. So what we can say is that the surface area of the new object is equal to K squared times the surface area of the original object. That goes back to the same thing we said about area, that it's two-dimensional, so it gets a 2 in front of that K. So when we scale up a three-dimensional object, the three-dimensional measurements, and let's clear this ink. I had a quick button for clearing ink, and I don't know where it is. You guys can probably do this stuff better than me. Oops. Okay. So when I scale things up in 3D, the one-dimensional, what are one-dimensional measurements? Well, there's a few of them. Length. And that includes width and height and depth and all that stuff, but length in general. Perimeter. Perimeter is just the sum of a bunch of lengths. Circumference. Once again, very similar to perimeter, it's the length around the outside of the circle. Arc length. Even says length in its name. So all of these things are one-dimensional measures. They're measures along a straight line or a curve in one dimension. Those will get scaled up by a factor of k to the 1 power. So if I have an object before and after, then the perimeters should be scaled up by a factor of k to the 1. The circumference should be scaled up by a factor of k to the 1. The lengths of all sides should be k to the 1. So what are some two-dimensional measurements? Well, two-dimensional measurements would be things like area. It goes in two directions. You got to have a length and a width, or a base and a height, or a cross-section 1, cross-section 2, whatever you want to call it. Area. Surface area, which once again is like perimeter. It's just the sum of a bunch of areas. Okay, surface area. And I may have to come back. I don't think I can think of any more right now that are two-dimensional. It's basically all the areas and surface areas will be scaled up at a factor of k squared. Whatever our k is, it's going to get squared in 2 dimensions. And then finally, the 3D, three-dimensional objects, the three-dimensional measurements that we could see scaled up are going to be volume, weight, okay, or mass. Might have been a better way to put it. Mass. Because weight is dependent on gravity. So, these would all be scaled up to a factor of k cubed. And this explains to me why when I was a kid and I could slam my Hot Wheel into the wall going, 20 miles an hour with no damage, why when I scale that Hot Wheel up to a real car, 20 miles an hour will do real damage. Because the weight is going to be scaled up also. If my new Hot Wheel is 100 times as big, if my real car is 100 times as big as the Hot Wheel, then it's going to weigh 100 cubed times as much weight. You know how much 100 cubed is? Well, there's 2 zeros, and we're going to multiply it together 3 times. So that means we should have 3 sets of 2 zeros. So it's 1 with 6 zeros. 1,000,000 times the weight. That is why I cannot scale up my little Hot Wheel car and make it work the same. And that's also why the dinosaurs had a very hard time living, because they're so much bigger, the weight is going to be excruciating on their bones. All right, and that is it for the scaling right now. And I'm going to go ahead and start working on the page. Thank you for watching the video.